This is a subset of data from the coronavirus information coming out of China, specific to in and around Wuhan. As you can see, there are 2,460 cases here that tested positive. We have information on age, and we have information on the sex of the person that tested positive, as well as whether or not the person died. This data, of course, is going to continually be updated. This is just for example. This is not going to be for publication, and it is a cleaned subset from information that is publicly available on a number of websites that are tracking this information. So this is simply for demonstration purposes for this course to talk about logistic regression. To get started, we would want to do a distribution on all three of our variables. So we can take a look at 2,460 in all three variables, both of our predictors, age and sex, and then looking at the 36 cases that have died. So there are things that you'd want to report, like the overall death rate here, which would be 1.5% from this particular subset. We'd want to look that we have a higher proportion of males, 56.1% compared to females. We've got a mean and median age that are very close, the youngest positive test being 1 year of age, all the way up to 96 years of age, with a mean and standard deviation of 45.4 and 17.4. In addition, we may want to do a number of bivariate analyses. So for those looking at an outcome of death, we may want to look at the distribution of male and female. That would be bivariate, and we would see here that the proportion dying is different, that we have less than 1% death for females and about 2% for males. We could also assess and look at the mean age by both gender and whether or not participants have died. And so since we have such a small proportion of people that have died here, this is squished all the way over, and that's simply a jumpism. Here on your display on how to uncheck x-axis proportional, and you would move this into the center here. For both of these, we simply like to look at the means and standard deviations, or we could ask for the quantiles, and we could look at the fact that our males and females are roughly of same age in the median and very similar in the mean, so we don't have to worry about age and gender being confounded. That's an epidemiological term and a statistical term as well. So it looks like age doesn't help us predict what gender someone is, and nor does gender tell us what age they are. So we can use both of them in a model together. We are seeing that those that have died are older, though not restricted to strictly an older population, though they are looking to be about 30 years older in median age compared to those that did not die. But again, we have a low proportion of death here, a low number of death. So all of these are to be taken with just a little bit of consideration for the low number of deaths out of overall deaths in terms of the evidence that we have. So now that we understand a little bit about our data, we may want to look at a simple logistic regression. So while we looked at dying and gender already, we can fit a nominal logistic and take a look at our first question, is gender helpful versus just the proportion that has died? And that answer is yes. Here is our whole model test, and then we can give a gender p-value, and of course we could look at an odds ratio here. So this is looking at dying, yes versus no, and then we have an odds ratio here for males. Males are 2.8 times more likely to die of coronavirus in this subsample of the population compared to females. And here is our p-value. One thing that I did not mention here, and you can see this by this little asterisk next to died, is that there was value ordering. Because no comes before yes in the alphabet, that would be the automatic logistic regression comparing the likelihood of dying versus not dying, we want to compare likelihood of dying versus dying. So under column information, under column properties, pick value ordering, and you simply would select yes and move it up above no. And that will give you the logistic regression that you're looking for. Now, if you want to say look at females versus males, that's the default. But if you wanted to look at males versus females, you could do the value ordering here. Okay, so let's go ahead and look at a simple logistic regression fit model for age. So put died, yes or no here, and let's put age and press run. And what we get here, you can see we have points for all of our all of the people that are included in this sample. The question being, is age a predictor of death? The answer is yes. Here is our overall p-value, and here is our age p-value. We may like to ask for the odds ratio here. And JUMP will give you two things. It's going to give you per unit change, so for every year older. It's also going to give you the range, but since we go from age of 1 all the way up to nearly 100 years of age, we're going to get a huge odds ratio here, and we can ignore that. What you really want to look at here is the unit odds ratio. And so for every 1 year older, the odds of dying are 1.1 increased. And here is our confidence bound on age, and you can see it does not include 1, and that is reflective of our p-value as well. So age is statistically significantly related to dying from coronavirus in people that have tested positive. We know that both gender and age are related, so let's go ahead and fit a logistic regression with fit model that includes both of these predictors, age and gender. And we will press run. Again, our main question is do these predictors do a better job of predicting death from coronavirus in people that tested positive compared to just the proportion of death alone? Our whole model p-value tells us yes, this model is useful. And if we go and look at our parameter estimate effects or our effect tests, both of these are useful. And so we won't interpret the estimates or the intercept here. Remember, this is in the log transformation. What we want to look at is the odds ratios. And so we get what we saw before here. We get the unit odds ratio for age. It stayed pretty consistent from age on its own. And we can look at the odds ratio here for gender. The default, because I didn't value order, was female to male. And the estimate being negative would tell you that females being protective. And if you go down here and look at the odds ratio, it is telling you that females are less likely to die compared to males. But what you'd like to report here actually is the reciprocal, or the odds ratio for male versus female, and JUMP gives both of them to you. Now you'll notice that you have the same p-value, because looking at female to male being protective or male to female being worse than for the odds of dying, it's the same test. So you would report the same p-value here, 0.0163, and then you'd be, since we're conditioning on death, we want to look at higher likelihood of death. So what we would report here is that age and gender are a better prediction of death from coronavirus in this subsample of those that tested positive in the Wuhan or near the Wuhan province in China. Our p-value for that is 0.0001. Both age and gender are statistically significantly associated with an increased likelihood in death, such that there's an increased likelihood of death if you test positive. For every 1 year older, you're 1.1 times more likely to die, and report this confidence bound. Males are 2.7 times more likely to die if they test positive than females. Report this odds ratio, this confidence bound here, and then also the p-value. And that is a multiple logistic regression compared to a simple linear regression. Remember, you will also want to report the proportion of death. So while it is more likely that males and older people die, the likelihood of death is only just higher than 1%, with males being more likely to die and older people being more likely to die.